Thanks for coming back to the next session. So our next speaker is, Chi Jin. We're excited to have him be here. And he's going to be telling us about, the recent work he's been doing on sort of decentralized algorithms for, multi-agent RL in Markov games. So I'll let him take it away.
Okay. Thanks for the introduction. My name is Chi Jin from Princeton University. And today I'm going to talk about our work on the V-learning, where it's a simple, efficient, decentralized algorithm for multi-agent reinforcement learning. Although the title is like a multi-agent reinforcement learning, but I also want to emphasize this algorithm, V-learning, is actually a single agent algorithm itself. Okay, and the reason we call it V-learning is because it's as simple as Q-learning, the well-known algorithm you probably know. But instead, we say it's multi-agent because we can basically prove for Q-learning, a lot of property is not very good for multi-agent, but for this V-learning instead, although it's as simple as Q-learning, but it actually has a lot of great desired property for this multi-agent reinforcement learning. It is decentralized, efficient, and we will also see later it actually breaks the curse of multi-agents. Okay, so hope this catch your attention. I will first do a brief overview of the result. Okay, first I want to also thanks to my wonderful collaborators. This work will not be possible without them. First is Yu Bai, who is probably in the audience, who is from Salesforce, and also my students at Princeton University, both Qinghua Liu and Yuanhao Wang. They are wonderful, wonderful collaborators. And also my collaborator Tianchen Yu, he is also a PhD student from MIT. Okay, first we will get to attention of what is the problems we will be focusing on in this talk. So the problems will be like those problems, like StarCraft, like hide and seek, or like poker, or like Go. Basically, we have two common characteristics about those problems. One is it involves sequential decision making. So it is a reinforcement learning problem. So we not only need to decide one action, but we need to, based on the feedback of the opponent or the environment, we need to make a bunch of decisions in a series. The second thing is different from the single agent reinforcement problems. Now we're not playing against some fixed environment. We're actually playing against some opponents, which possibly they can change their policies during their playing. Also, the opponent can even be adaptive. That is, I'm playing some policy. My opponent can realize, oh, I'm playing some stupid policy, and they can adapt it and to exploit my behavior. Okay, so this makes it a lot challenging. So this is also defines what is multi-agent reinforcement problems we're interested in. Basically, the multi-agent reinforcement learning problems can be considered as a combination of two categories. One is a classical game theory, where we're dealing with players playing against each other, and we want to find the Nash equilibrium or some other equilibrium. The other thing is like the reinforcement learning. We need to deal with a sequence of decisions, and we need to make like the good decisions, good actions in the next step based on the feedbacks in the previous steps. So this gives a multi-agent reinforcement learning. And specifically, in formalism, we will consider a model of Markov game, where we kind of like following the reinforcement learning. We know reinforcement learning, we usually study the model called the Markov decision process. So Markov game can be considered as a standard extension, multi-agent extension of Markov decision process. We will specify what is exactly like the definition of Markov games later, but for now, you just think this is a multi-agent extension of Markov decision process. And in the literature, it's also known as stochastic games, which was proposed like 50 years ago. So a lot of things in the multi-agent reinforcement learning on Markov games can be adapted from like our results from Markov decision process. That is a single agent version. We combine with the games and deal with and we extend it to the multi-agent version of games, Markov games. However, there are several challenges which is unique in this multi-agent reinforcement learning, where single agent reinforcement has absolutely no idea how to address them. One such unique challenge is so-called cursive multi-agents. If we look at the size of games, where if we have like n players, we need to like specify what is the utility for the single player I. The utility is going to depend on all the actions of other opponents. So this size or the complexity of game is actually going to grow exponentially with number of agents. So this is what we call cursive multi-agents. And then we will see later, if we naively adapt a single agent reinforcement learning algorithm here, we're actually going to pay some complexity that is exponential in this number of agents, which is quite undesirable. Like if we want to design some multi-agent system for like 10 drones or 20 drones, that's going to be disaster. Like we don't have enough samples to train good policy for those kind of systems. The other thing is about unique challenges about the centralized algorithm versus decentralized algorithm. In a single agent learning scenario, there's no such difference. Every algorithm is like either centralized or decentralized, it's the same thing. So the decentralized algorithm in a multi-agent system means we hope we can have some algorithm so that all players, all agents, just simply run the same algorithm independently. Okay, they just need to run the same single agent algorithm independently, like as if they don't really know whether there are some other players or not. And the benefit of doing such things is it's kind of like agnostic against other players' actions, and also it can be implemented much easier because you just need to implement a single agent learning algorithm. And finally, we can like reduce a lot of communication because it's each agent just run independently, so it doesn't really require any communication. So the main question in this talk is, can we actually design a decentralized multi-agent reinforcement learning algorithm that breaks the curse of multi-agents? So the two challenges we talk about here is one, decentralized algorithm, and the second one is the curse of multi-agents. It sounds like a very fancy goal we want to achieve, but since I present the question here, of course, the answer of this talk is yes, we provide an algorithm that is able to achieve both of them. Okay, so I will just quickly brief overview about what is our results. The results is we need to get these results based on a newly designed algorithm, such called V-learning. Okay, as I mentioned in the first slides, V-learning is actually a single agent reinforcement learning algorithm, so it can learn the single agent Markov decision process. Okay, and it was proposed in our early work with Yu Bai and me and Tianchen Yu in 2020. So a couple of characterization why this algorithm is able to solve both challenges. First, about decentralization. We've proved that in multi-agent reinforcement learning, all we need to do is we just run this V-learning algorithm, which is a single agent learning algorithm, independently for all players. Okay. We don't need to any like centralized scheme or like collaboration or like any connections, or we just run them independently. So this perfectly achieved the decentralization. The second one is about break the curse of multi-agents. We actually can prove as well, we will handling all the perspective of learning, which including planning, estimation, and exploration. We will explain later what each terminology means. And we will handling all the perspective of learning in those number of samples. Okay, this is a max AI, where AI is number of action of each player. So what are we going to cost is only the maximum number of actions for each player, instead of the product of number of actions for each player, which is typically the size of the game, or like the game matrix, or like the Q values, if we will specify later. So we know this is like the curse of multi-agents, which kind of grow exponentially with number of players, but this one does not grow with number of players if all the players have the same number of actions. So this breaking the curse of multi-agents. So I want to also emphasize the meaning of this work, and I will say V-learning is the first, but also remains the only class of algorithm even till today that can provably address both challenges in Markov games.
Sorry, just a clarification question. So you could run two learning algorithms independently for all players. So can you clarify what's the challenge?
You can run it, but you will not be able to. So we need to prove the results. So we need to prove we will actually converge to Nash equilibrium. Yeah, formally converge to Nash equilibrium, converge to correlated equilibrium, and Q-learning, we cannot prove something. That's a very good question. Yeah, I think the provably is important. Provably address those challenges. Okay, that's basically the overview. So without further ado, we will, any questions so far? No questions, I will just directly go to the formulations and objective, like what exactly we're talking about learning. So we say we will study the multi-agent reinforcement learning problems under the formalism of Markov games. Okay, this Markov games is has several components, which is a set of. It's similar to a Markov decision process, which we have a set of states as, and for simplicity, we view our work as a first step in dealing with Markov games. So we studied a simpler setting, which is a tabular setting. We have a finite number of states and a finite number of actions. So different from Markov decision process, here we not only have a single set of actions for player, we will have multiple set of actions. So AI donates the set of actions for the agents, for the ith player. And the two key components of Markov games. One is transition. Transition is about your transition probability starting from the current states to the next states. And the important thing is it's conditioned on the joint action. Okay, we will see this action with this like bold folder means the joint action of all the players, A1 to AN, that we need to put out the player. All the player will play the action simultaneously, and then we will transition the system from the current state to the next states. And we will also have a reward for each player. So each player will have different rewards. So this is like a general formalism about general sum Markov games, where we use I to denote the reward received by the ICE agents. H means the reward we're going to receive at step H, okay, and depends on the current states as well as the joint actions. So finally, we consider episodic setting. That means we just consider the game where we always stop in H steps. H is the horizon or the length of games. Yes.
Position is depending on the stage.
On the current states. Also on the stage, yeah. Also on the states. On the current steps, yeah. So basically, for different steps, we can have different transition. From S1 to S2, we can have some transition that is different from S2 to S3.
It's not stationary.
It's not stationary, yeah. It's non-stationary. It's kind of like a little bit more general than stationary setting, but we can definitely also handle the stationary setting. Yes, Milan.
Of Nash equilibrium is hard. So when you say converge to Nash equilibrium, what do you mean?
We will talk about that objectively later. Yeah, that's a good point. Yeah.
Sorry, just to clarify. I think with Shapley's work zero sum, is your work zero sum?
Oh no, this is not zero sum. I think Shapley's work can also be extended to like general sums.
Yeah. And did you just say the game is finite? Finite horizon?
Finite horizon, also finite states, finite actions. Okay, so everything is finite. Okay. Okay, and we will just quickly introduce what do we mean by policy and value. Both of the concepts follows very similar to the single agent reinforcement learning setting. The policy for the ICE player is we just map that from the current states and which steps we're taking this policy to the distribution over actions. Okay, so here the randomized policy is very important because if we find an equilibrium, most of them are like a randomized policy. So it's a map to a distribution over actions instead of just a single actions. And also we can define the values where we have two different values. One is a V value, the other one is a Q values. Similarly, we have values first, each value will for each player I, and it depends on some policy pi. So this value will define as a cumulative rewards, that is all the summation of the rewards in the future if all the players are playing again according to this joint policy pi. Okay, so this policy pi actually decodes all the policies of all the players. And starting from the current state S or state action SA, it depends on like whether it's Q value or V value at step H. Okay, just same thing as single agent reinforcement learning. The only difference is like now we have index I denotes the utility for ICE player, and the policy is gonna depend on all the players.
Just another clarification on the history. So you can condition on what? On what's H in square bracket?
This is like okay. So here I'm just writing very simple. This is just a 1, 2, 3, 4 like index of steps. But you're right. You can also have a policy, the general policy. Not this is like Markov policy, but general policy can depend on everything happened in the past, like not only the current states, but also everything happened in the past.
Theoretic definition of a strategy. So
right.
You're not departing from that for the moment. Is that correct?
Right. I think here for simplicity, I just defined the Markov strategy, which only depends on current states. But later we will also deal with a policy that depends on the entire history. You're right. That's the basic definition for the games, strategy for the games. Okay, and I will just also quickly clarify what is setting we're talking about. In order to learn the equilibrium or like the good policy for this game, so there are several different strategies. One is like we just learn from the experts. And this one is not what we're using. There are several drawbacks of such approach, like it's expensive. It's also slow. Like expensive, we need a lot of money to hire the experts, and slow because a computer can run a lot faster than humans. And also it's highly depends on the level of experts. Like if expert is world champion, probably it's okay. But if expert is like some mediocre player, then probably whatever the policy we learn may not be that good. So what we will do instead is we consider a setting of cell play. So we just completely eliminate the role of human in this process. We just learn by ourselves. So we will control all the players and we just learn the best policy by ourselves. So this is called like cell play setting is our focus. So to be clear, like our setting is like we just learning from interactions. That means all we have is just have a game. Like suppose a real scenario, we just bought a game. Okay, this is all we have essentially. And we are allowed to control all the players. Like for StarCraft, I can buy 2 copies of games. So I can open up 2 computers. I can control 2 players. Like I let them just play against each other. But what we can do is we can only play games as normal player do. Like we cannot crack the code. We cannot see what is happening behind the scene. We have to play as a normal player do. That is play the game from the start to the end. Okay, that's it. We're not allowed to cheat. And we can play the game multiple times. This is setting. And our objective is after we controlling all agents and play the game for multiple steps, multiple times, we require to find the optimal strategy. We'll define what is optimal strategy do we mean here. And we hope we can become the best player. Like for StarCraft, we want to be the world champion or something like that. Okay. Yes. Yes, so I think so we are allowed to control all agents. So there is a difference between centralized algorithm versus decentralized algorithm. So in theory, we allow centralized algorithm, which have centralized controller, just to control all the agents and planning for all of them. And our algorithm design, B-learning, is like a decentralized algorithm. That is, although we allow to control all agents like together, but we just let them run independent algorithms. So yeah. Okay. I just want to clarify, like this learning from interaction setting has like 3 major components about learning. The first one is planning, that we need to compute the optimal policy based on the known model or values. Okay, this is like a very basic part that basically assume we kind of like know the entire games. However, in reality, we don't really know what is the rule of game. We have to learn these games from playing. That is, we need to estimate the model, like transition and reward, and we also need to estimate the value based on the collected data samples. Like we need to do some fitting to estimate the model. And finally, this also assumes we have some collected data samples. And a very important thing that distinguishes this work from a lot of other works is we also address the exploration. That is, we don't assume we magically have some like very good data samples that is covering a lot of like all perspective of the games. Instead, we will just strategically trying to design algorithms so that we can collect informed data samples to finish the estimation step and then finally finish the planning steps. So we'll deal with all 3 components of learning. Okay, so this is about our setting, like how we want to find the optimal strategy. And the other thing is, what is the optimal strategy we're trying to find? Okay. So I want to emphasize, although we're saying like we just want to find the best player like in the world, but actually the solution concept of the game is much more complicated than like single player setting where we have like linear relation. We say one policy is just better than the other policy in terms of value. Here, for example, we can consider a game like rock, paper, scissors. The strategies may not have linear relation, like it has some cyclic relation. For example, I consider the strategy A as rock, strategy B as like a scissors, strategy C as a paper. So we will see like strategy A, B, strategy B, strategy B, B, strategy C. But on the other hand, strategy C also B, strategy A. So we have a cyclic structure. So if we just directly say like who is the best or like who's gonna beat everyone like with some large margin, this is not possible. And furthermore, this is about purely about competition. So we cannot just define some linear relation. And the second thing is about general sum games. We might even prefer some collaborative or correlated strategy. We will say later that is in general sum, we're not necessarily just competition. We might have some collaborations. So we might face some scenario that is a win-win to both players or for multiple players. And we want to develop some correlated policies. So this goes back to the equilibrium or the solution context we're trying to find. So the first thing is about Nash equilibrium. Nash equilibrium is the product policy. That is, a product policy means the policy is independent for each player. That is, the randomness I'm gonna play for my policy is gonna independent from the randomness the other player plays. And so this Nash equilibrium defines the strategy so that no player can gain by deviating from her own policy. That is, I will not play pi 1, I'll play some other policies while fixing other players' policy, while the other player are just playing according to those policies. Like in the rock, paper, scissors case, we will prove actually Nash equilibrium is just playing all actions with 1/3 probability. And in the 2-player zero-sum games, the Nash equilibrium have further a more strong meaning to this kind of scenario. That is, it's also an optimal policy when always facing the best response. That is, I always assume my opponent knows me perfectly so that he can place my best response. Then Nash equilibrium is the best in the minimax sense. That is, if I always play rock, my opponent can play paper so that it can like exploit my weakness. Then the 1/3, 1/3, 1/3 strategy, that is, no matter my opponent, how my opponent exploiting, I can always draw with my opponent. So this is like the minimax best policy in this two-player zero-sum game scenario. In the general sum scenario, we're saying we might face some scenario where we actually will have the win-win situation, so that we might prefer some collaborative strategy. We will also consider a very simple example that is a modified version of rock, paper, scissors. That is, if two players play different actions, we will just like judge according to the standard rule of rock, paper, scissors. But in case of the draw, that is, both players play the same actions. Let's assume we gave both players reward 1. Okay, so instead of just draw, we will give both players reward 1. So in this scenario, we can see both players will prefer to play the same actions actually over they compete with each other. So in this scenario, a correlated strategy, that is, we're gonna play uniformly over either two players play rock together, or two players play paper together, or two players play scissors together. We know this is no longer independent policy, that we cannot just implement this policy like by both players play independently. We have to have a centralized player that tells both agents like what is the current policy you want to play. Okay, so this defines a so-called first correlated equilibrium. Instead of a Nash equilibrium, which is a product policy, here is a correlated policies, where again, no player can gain anything if other players are fixed. And the only subtlety here is if I deviate from my correlated policy, whether I can observe like what other player, because we know like when we implement this correlated strategy, we need to have a centralized player that instruct all the player like what is current actions you need to play. So there's a subtle difference whether we can observe what is action I'm gonna play in the current iteration, or I cannot observe it. So if I can observe it, it's a correlated equilibrium. If I cannot observe it, it's a coarse correlated equilibrium. So those are two notions of equilibriums we consider for the general sum games. I just want to quickly summarize all the relation between them. So the relation is like Nash is actually the smallest set. So we can say Nash is a correlated equilibrium, and a correlated equilibrium is a coarse correlated equilibrium. And we kind of motivated this correlated strategy by in a general sum setting, like we want to have a win-win. We would like to have some collaborative scenarios. So we might prefer this correlated strategies. And also comments like which also mentioned by Elad, that is in a general sum games, that is beyond two-player zero-sum games. As long as it's more than two-player or it's not zero-sum games, we can actually prove computing Nash equilibrium is PPAD hard, which is we don't really know. We have no polynomial time algorithm for computing it. However, on the other hand, the general notion CE and CCE, we can always compute it in the polynomial times by linear programming, no matter it's like a zero sum or a general sum. So our objective in this talk, because this computational constraints, we will care about the Nash equilibrium only in the two-player zero-sum game scenario, and in a general sum scenario, we will opt to this correlated equilibrium and a coarse correlated equilibrium for more than two players. Okay. So after talking about setting, we will talk about the algorithm side and ideas, how we're going to find this equilibrium. So the first thing the first idea we'll consider how to find such an equilibrium is we want to adapt the single agent reinforcement learning algorithm, as we mentioned earlier. So basically we have three components of learning. So for learning in a single agent scenario, we just use a Bellman optimatic equation. Here we can also do something similar, just replace the max by the min-max or by some like a general equilibrium in this scenario. And the most important thing is we will estimate the transition of the Markov games or the Q value of Markov games. Okay, either like similar, like in a single agent algorithm, this is like value iteration or Q learning. So we can also have the multi-agent version like Nash value iteration, Nash Q learning, or some general version of equilibrium Q learning. In our previous paper, we can do that. And then finally, for exploration, we just use the standard upper confidence bounds for exploration in the reinforcement learning. So this is the basic results we can prove when adapting this single agent reinforcement scenario to this Markov games. We can say this value iteration, that is based on estimated transition, combined with upper confidence bound, This algorithm can actually learn an epsilon version of Nash equilibrium CE and CCE. The only thing is like this Nash equilibrium is not computationally efficient in this scenario, but we can learn it statistically efficiently in this amount of episodes of play. That is, as long as we play this amount of games, we can find this equilibria. The amount of sample complexity can be understood in terms of dependence on this H, which is horizon, S is number of states, and AI is number of action. So here we see this is like a curse of multi-agents. So we pay something exponential in the number of players. And finally, 1 over epsilon square, where epsilon is like the suboptimality of the approximation of what is your final equilibrium you're trying to find. So the major bottleneck of such an approach where we want to adapt in single agent reinforcement learning here is all the single agent reinforcement learning so far relies on estimation of some transition or the Q value, where we know both transition and Q value will depend on the joint action, which scales as some product of AI, which is like a big bottleneck we cannot circumvent. If we cannot use this kind of approach if we want to break this curse of multi-agents. So we just want to remind you, like we briefly mentioned earlier, like we have 2 unique challenges in this scenario. One is a curse of multi-agents. We want to have some complexity that is scaled with the max AI instead of product AI. So we want to have something polynomial in the number of players. And the second thing is we want to have decentralized algorithm. This algorithm, like the algorithm I presented in the earlier slides, depends on maintaining the joint transition and the joint Q value. So this thing actually requires a centralized agent that is able to calculate this Q value for all the players and then playing according to that kind of thing. So it's a centralized algorithm. So we want to address both challenges. Okay. So in order to deal with this complicated goals to achieve like both challenges in the Markov game scenario, we would like to first ask ourselves, how do we address both challenges in a simpler setting of normal form games? Okay. Normal form games is a games where we study a lot in the classical game theory. Basically, we can consider normal form games as a special case of Markov games, but without any transition or states. So basically, we just say the utility of all the player I can be represented by a tensor that is function depends on i's player and only depends on all the actions of each player. So in this kind of scenario, like we can say if a 2-player zero-sum games, we can basically just represent the utility as a matrix of 2 players. So the answer for this scenario is actually very simple for normal form games. We can just run no regret algorithms independently for all the players, where the no regret algorithm was designed for adversarial bandits. Okay. So I just want to clarify what do we mean by adversarial bandits, also to fill you in if you don't have any background on this adversarial bandits. Adversarial bandits basically is a problem. So we have 8 different arms, and we want to pull the best arms like to minimize the regret. We will define later. So the interaction protocol is something like this. At each round T, the agents will first pick a policy that is like a probability over all the actions. And that is what probability I'm going to put arm A, what is the probability I'm going to put arm B. And the adversary will pick an adversarial loss. Okay, this loss can actually adapt to what I played earlier, can also be adversarial, can be whatever they want. So this is a power of this adversarial bandits because this loss has a lot of power. And then the agent just playing an action that samples from the policies I picked earlier. And then the agent will receive a loss, that is the adversarial loss, but only on this component, only on the actions I played. I do not receive feedback on a loss of other actions I have not played. So this is an adversarial bandit scenario with bandit feedback. A very simple algorithm for this adversarial bandit, no regret algorithm for this adversarial bandit is called follow the regret leader. So basically, we will estimate the entire loss based on the importance weighting. Because we only observe the bandit loss, that we only observe the loss for the action I played at round T. So how I'm gonna estimate the entire loss? I'm gonna based on the importance weights. That is, I'm gonna have the loss on the action I put, and with indicator whether this action is the action I put, and reweighted by the probability I'm gonna pull that action. And with this importance weighted loss, we can just do the updates based on the exponential weights, update the policy. So the probability I'm gonna play action A in the round T is gonna proportional to the exponential of minus some eta T learning rates and the summation of all the previous loss I have. That is, if I have a lot of previous loss, estimated loss, then I will have a lower probability to play that action. If I have a very little loss for this action, then I will have a lot of probability to play this arm. So the important thing about this regret and this algorithm is like we have this regret guarantee, which says this is like the entire reward I'm gonna receive in expectation. The mu t is a policy I played at round T, and the LT is the loss at round T. So if we compete against the best policy in hindsight, that is, if I L1 to LT already fixed, and I choose the best policy if I given L1 to LT. Okay? And this L1 to LT also can be adversarial. And we're gonna prove this regret will not scale with linear with like the horizon T, but it will scale with sublinear with T. So in particular, we can prove it up to some logarithmic factor. It's just square root of AT. A is the number of arms we have for each player, and T is the horizon. The very nice thing about the no regret algorithm is we can immediately transform this no regret algorithm to equilibrium learning. That is, in a two-player scenario, two-player zero-sum scenario, for example, we can measure the optimality with this duality gap. If you're familiar with online learning, I guess this will be very familiar to you. So basically, the duality gap is we measure the against the best response, what is the performance of the average policy of the opponents versus the average policy of myself. And this difference is a duality gap, measures how far away the average policy of nu t and average policy of mu t to the Nash equilibrium. So what we can do in this scenario is we can plug in a term that is summation of mu t q nu t, and also subtract this and plus this q mu t nu t. And so this will be equal. But then we can decompose this duality gap into a regret of the two player. So this is a regret of the first player and a regret of second player. Yes.
Do you get low regret? Does the best optimal best policy in like full tabular MDP just from a single agent perspective? Do you get that efficiently?
No, you cannot. We will talk about that later.
Kind of issue there.
Yeah, in the games you cannot do it. This is purely for normal form games. Yeah, in Markov games you cannot do it. We'll talk about it later. So the very good thing is now you can decompose the duality gaps into two parts of regret. And then the power of no regret learning is we don't care about what is this loss. This loss can be adversarial. So of course, cumulative is one of the possible loss. So we can just directly apply the no regret results, and which tells me my duality gap will only grow with this thing, like square root of A1 plus A2 times T. And if we average over the number of iterations, this will give me 1 over square root T convergence. Okay. So that is, in summary, we can say this, if we play the uniform policies of mu t and uniform policy of nu t, and both players play follow the right leader, or like no regret, any no regret algorithm, we will be able to find the Nash equilibrium in two-player zero-sum games in roughly this number of samples, that is A1 plus A2. Or you can also just say this max A1, A2, because in the two-player, like max and plus is like the same thing. And I will also not be very specific, but basically with the same tricks, you can actually prove in general sum games by running no regret algorithm independently for all players. What you can do is you can like couple in the policies they play at each round. So mu1t, mu2t to mu-mt. And then I uniformly sample t from this like entire iterations. So this one will create some correlation among those policies. Although at each round, each player play independent policies, but when you uniform sample from like what rounds you're gonna sample it, so it becomes correlated policy. So you can prove this policy will eventually converge to coarse correlated equilibrium, and the number of samples you need is only the maximization of I and AI. So that achieve our goal of like breaking the curse of multi-agents. Okay. So this part is basically says to solve both challenges in the like normal form games, the simpler setting, we just run no regret algorithm and everything becomes very easy. However, the very question, like as Elad asked, is whether I can just directly run no regret learning algorithms for Markov game. In particular, what do we mean by no regret learning algorithm? Is like we just place against some policies pi t, and if I kind of compare with the best Markov policy, or best policy or even best Markov policies. And in hindsight, can I achieve the regret that is a polynomial in everything else and the sublinear in T? Yes.
The previous thing that you explained, additionally, it depends on the tensor size, right? Not only on the
On what?
The tensor of all possible actions or whatever. Like
Tensor.
yeah, like what's the computational complexity of this procedure?
No, it doesn't. So basically, everyone just run for the regular figure. So the condition is just for the regular figure.
Over their own actions?
Over their own actions. Yeah. So it doesn't really care. Okay, so the game probably need to compute what is the loss and send you the loss. As long as you have that, and then you don't need to do anything. So which pair?
So the policy space here is what? Over I mean, you have to be polynomial in the number of policies.
The policy here is just each agent is a distribution over their own actions.
Okay.
And we say we do the correlation here by just uniformly sample from T. So each run is independent. So the representation is actually also very succinct. Okay. Yeah, so can we write this no regret learning algorithm for Markov game? We want to achieve the sublinear in T. So unfortunately, the sad news is this is information theoretically impossible. So we have a theorem which says there exists two-player zero-sum games. In our very recent work, we show this exists two-player zero-sum games, where the regret, if we want to compete against the best fixed Markov policy, okay, we don't even compete with some general policy, we just compete with Markov policy. In hindsight, the regret is at least minimum of T, number of rounds we play it, and also 2 to the H. That is, we're gonna suffer a regret that is exponential in the horizon. So this thing only appears in the Markov games where we have this like sequential structure, so we have H steps. In normal form games, this is just 1, so this is obviously good. So the key observation here, why such kind of thing is information theoretically impossible, is because in Markov games, my opponents can not only temper the reward, but also can like screw up the transition. My opponent can actually change the transition. So we can actually prove other player can encode some very long-term correlations to make these games very complicated if we just view these games in terms of in the perspective of just one player. So we can actually say Markov games can simulate a POL-MDP, a generic POL-MDP, if other players are allowed to play any history-dependent policy, okay, not only Markov policy. So if we say this is cheating, like we don't allow other player to play the history-dependent policy, we only allow other player to play Markov policy, then we can also say they can simulate a latent MDP. Essentially, we have a multiple MDP, but we're going to sample one at the very beginning with some unknown probability, and we don't know which the identity of our MDP. And we can actually simulate that with several Markov policies. Yes.
Yes.
This one?
Okay, so here. My issue is so is this, you say samples here and you talk sample complexity, like when I think of no regret learning algorithms, I think of like iteration.
Iteration, yes. Exactly.
So is sample complexity what you mean here in iteration complexity?
Yes. Yeah. Sample complexity means like if we want to find epsilon optimal CCE, what is number of iterations?
And you're just hiding polylographic.
Polylography.
Okay, cool, awesome.
Okay. So we can actually show, because both of them are like a case of POL-MDP, so like it has a partial observability. It's very difficult to learn those kind of things. It's like long-term horizon. We can easily prove there's some known existing like a statistical harness for POL-MDP and latent MDP, which basically says you need to pace this exponential in terms of horizon to learn this in general. So now we know for Markov games, no regret learning is not possible. So what we should do? We should do no regret learning instead. So we should have some algorithm which should bypassing the no regret learning. So we note a very subtlety here. Very important subtlety here is like so far what we say is once we have a no regret learning algorithm, we're able to give you like an algorithm that is able to find the equilibrium very fast. However, our final goal is we just want to find an equilibrium. So it doesn't necessarily mean we have to have a no regret learning algorithm. So what we're gonna do for Markov game is we will focus on this here, finding equilibrium, but we will not have a no regret learning algorithm because this is not possible. Okay, so this means that despite no regret learning is possible for Markov game, we can use this idea. So we will use the principle here to design an efficient algorithm that is only able to find equilibrium. This is like how we design this V-learning algorithms. So just quickly go over the algorithms. It's actually quite simple. So the first step is very like we have a k iterations and we have h steps, and we just take some actions according to my policy, observe rewards and next states, and we update the counting where we kind of maintain a counting for each state. So all the steps are very standard. So the only key steps are those two steps, which noted as blue and red. So this blue step basically says we're going to have an incremental update on the v-value. Okay, so the v-value is going to be updated as a 1 minus alpha fraction of my previous v-value and plus alpha fraction of the new updates I observe, new samples I observe, that is a current reward I observe, and the value of the next states, and plus some beta, which we will have some bonus in estimating the value, which we just use halving bonus. It's a standard thing in the upper confidence bounds. So the important thing is here we have incremental updates on the v-value instead of a q value. We note like the q value have some bottlenecks, which will depend on all actions. The size of q value will depend on all actions. However, the v-value only have a size of s. So this is a very important thing, how we get rid of this exponential dependence on the number of actions. And the second thing is the benefit of q value, like in a single agent setting, why we use q value instead of v value is because q value can give you a policy. We just do an argmax over actions. We have a policy for q learning. However, here we just have v values. We have no policies. So this is why we will use no regret learning algorithms to compute the policy for us. So what we're going to do is we're going to run the no regret learning algorithm for each state sh. Okay, and we're going to feed the actions I put and feed the fictitious reward or the loss I receive, that is RH plus VH plus SH plus 1. So this one will make this no regret learning algorithm pretends is playing an adversarial like a Bandit problem for each state differently. So we just use this algorithm to give me a policy. We can use like exponential weight updates, follow the regularized leader, and this is just the odd algorithms we have. And the learning rates, the choice of learning rates is the same as Q learning. We have, this is like 1 over T, roughly 1 over T, H over 1, H over T. So the key steps is two things, as I emphasized. One is incremental updates on the V value instead of Q value. So this is why we call it V learning instead of Q learning. And the second thing is we will run no regret learning algorithm for each state. So those are the key ideas of V learning algorithms. Yes?
Just to clarify that V is one global V, not a per-agent V.
V is we have a V pre-iteration, so we're gonna update V pre-iteration. So this is a V at round T, and this is round T plus 1.
There's one V for the entire game, not one V for each agent, right?
One V for entire game, yes. No, actually, sorry. This is like a V learning is a single agent learning algorithm. So we will have this V is only for the agent itself. So different agent will have different V like a V value. So here, this is all I talk about single agent learning algorithms. So okay, I will just briefly talk about guarantees. So I introduced the V-learning as a single agent learning algorithm. For multi-agent setting, we just run V-learning independently for all the players. Okay. And we will use the adversarial Bandit subroutine, which is a follow regularized leader we introduced earlier. So we can prove in our early work that is in two-player zero-sum games, the V-learning with follow regularized leader is able to find epsilon Nash equilibrium in this amount of episodes. So the important thing is now we no longer pay something product of A1, A2. Now we only pay the max A1, A2, or like A1 plus A2. And in the later work, we can also prove in general sums games, we can extend these results to finding epsilon coarse correlated equilibrium in this amount of episodes. So this amount of episodes is no longer product of AI, but as max of AI. So I just want to finally emphasize that V-learning, as I said earlier, V-learning is the first and also remains the only up to today, the class of decentralized algorithm that are able to break the curse of multi-agents. So if we'll talk about a multi-agent reinforcement learning algorithm that is a polynomial in everything, but also number of agents, I think V-learning up to now is the only algorithm that are able to do polynomial for everything. Yes.
Can you go back to the algorithm? So now what you're doing is you're running this Bandit algorithm, right?
For each state.
Pretending it's a Bandit. So you have to relate the best in hindsight kind of changes because you're running no regret And the best in hindsight is going to be with respect to these losses that you construct.
Yeah, that one is only in the analysis though. In the algorithm, you don't need to compute what is the best in hindsight.
No, I'm not saying you have to compute. I'm saying like in the analysis, you have to relate that to
the fictitious loss here. Yes.
From the fictitious loss, you have to relate it to the actual gain, right? Is that easy to do, or is that?
It's easy to do because we only do it state-wise. We're not doing it like for the entire Markov game because it's only state-wise running on adversarial Bandit. So we don't have anything about the sequential thing. So we can just use the standard follow the right as leader analysis. A slightly more modified version.
Okay,
yeah, we can.
My question is different, but we can talk about it.
Yeah, sorry. Maybe let's have a quick one because we need.
Could you explain why you're using the v function instead of the q function? Like, why couldn't you just express that as a q function update? And could you also tell me what is episode defined as? Is that like when every time some? Like,
episode is like when you finish a game of StarCraft, for example, you just like play 1,000 steps and the game ends. That is one episode. And we, as I emphasized, we use q value here because q only depends on s. Well, v depends on s. Well, q depends on s and a. A is like joint action. So if you have joint action, you always pay something exponential, like something product of AI. Well, here the v value is only depends on s. So kind of we get rid of the product of AI. We can't break the curse of multiple.
It's just because you only include in that second red step. So you say you're ignoring all of that exponential stuff or all the type of stuff. Okay.
Not ignoring, but we're not, we don't incur that kind of thing. Okay, probably we can talk about that a little later. It's a little bit behind. So this is the first and remain the only algorithm that is solve both scenario and SSL polynomial. So just a very quick place says we can also deal with a coarse correlated equilibrium. The only thing is we can also deal with a correlated equilibrium without coarse. The only thing we need to change is instead of running no regret algorithm, we will run no swap regret algorithm, which is a stronger definition. Instead of competing with the best policy inside, we'll compete with the best policy in the sense like, what if I'm gonna swap all the iterations I play action A to action B? I can basically swap all the actions to different actions. So in a standard no regret algorithm, we have to swap all the actions to a single fixed action. Now I can swap to different actions. So this is definitely harder, and we're able to show that we just change this like adversarial bandit some routine with a follow right leader with swap with some swap type of modification to the follow right leader. We're able to find epsilon coarse correlated equilibrium. Also in this max AI thing, the only thing is like we pay this square because we need to deal with swap. It's kind of a little bit harder. I just want to finally give some bibliography notes about. Could we just maybe post it to the very end of the talk? Yeah. So the very first work we proposed deep learning is back in 2020, and then later after 1 year, like the current work realized we can extend this results to like finding CE and CCE for multiplayer zero-sum games. So we have this general version, which is for deep learning, and also there are concurrent works by Son made by and also now and Bassar. The major difference, I would say this one didn't deal with CE, and the other thing is probably just the algorithm slightly different, and also the rate we get is a little bit sharper in terms of H dependence. Similar to what? All of them use a V-learning style algorithm, yes. So that's why I claim this is like so far the only style algorithm that able to achieve this kind of thing. Okay, I just want to give a summary of what we presented so far today. So in two-player zero-sum games, we can find this in terms of Nash in this thing, and in CCE we can play for multiplayer general-sum games. And the important thing is we only pay A, where A is max AI. We no longer pay some product of AI, so we're not paying cursive multiagents, and it's decentralized algorithm. So the conclusion, we have the first algorithm that is decentralized and break cursive multiagents. There are several future directions I want to say a little bit. First thing is H dependence. So we have H to the fifth, which is not very sharp. And the techniques to shaping this H dependence is a little bit different from the standard reinforcement learning, which you can use Princeton inequality and some other variance reduction techniques. Here, because we use no regret algorithm, so we need to use sharper bounds on the no regret algorithm, which involve different techniques. Second thing is about output policy. Although the algorithm is a little bit is quite clean, but the output policy I haven't mentioned is a little bit nasty. We require some nasty mixture of output policy. We can prove that policy is Nash equilibrium or CCE. So we're able to have some clean output algorithm for the two-player zero-sum setting. And for the multiplayer setting, I believe later by that's Clark's group, they have some Markov output policy, but they incur some quite suboptimal dependency on all the other states and number of actions. So how we get clean output policy while have like a sharp complexity is kind of still an open question. And finally, how to combine this with a function approximation and how to design this towards a practical algorithm, because in practice, hopefully we combine this V-learning with deep neural networks. That kind of thing is still quite open. Okay, and we also have some blog posts about the multi-agent reinforcement learning written with Yu Bai, and I want to have, this is like the link. Let's finish my talk. And thank you very much for attending.
Thanks a lot.
So I can see the local red. I mean, I get the converged state, but the V values for every agent, they somehow need not to cycle or kind of like converge to an optimal thing with respect to one another. I guess this was Edgar's question, maybe also. So how do you ensure that thing happens? So they don't cycle somehow?
I believe we don't actually show the V value converge to optimal. We show actually for per state. For per state, we actually well, actually, I think we do show like this. This is like essentially gives you an upper bound because we have this confidence set, and this upper bound will eventually converge to V star in some regret sense by this adversarial bandit, because we can just directly plug in the guarantee of the for the regularized leader. We're able to say whatever the policy I play in this round is going to compete with the best policy in hindsight, and that best policy in hindsight eventually we're going to relate that with the best, like the exploiting policy in the like duality gap in the final regret guarantee we have. Essentially, we need to bridge that kind of thing in the.
I mean, I can compete with the best in hindsight, so particular V value for sure. But this V value can change along the way, right? When all the other players do. So that's kind of the part I don't. Maybe it's complicated.
It's kind of complicated. Yeah. Yes, you're right. And in a general sum setting, you cannot show this is like converging to a single value because you have multiple CCE and C, like they're not unique. So you might jump from one to the other, but eventually we can see asymptotically it will converge to. It's kind of like something similar to this to this thing. Essentially, for general sum mode learning, you can also show this one. We will converge to CCE, but it's just one single CCE.
So for that to happen, the update rule that you wrote on the V value update, the next slide, this line number, whatever, the blue line there, that needs to be some kind of low regret with respect to the V value.
That's also true. The reason is like we can pick the learning rating will be this. This is H over T instead of 1 over T. If it's 1 over T is just average, then this is not very good. So H over T will heavily favor the later updates. So it somehow has a mechanism to forget what is happening in the past. So that's why it has some no regret components in it as well.
Maybe a related question is kind of what is the notion of like optimism that this choice of V that you're doing satisfies?
We can prove this. You mean like what is the upper bounds on this thing?
Yeah, so I mean, like, I guess, like, so why are you adding beta T, right? Like, you're adding beta T to try to make this thing optimistic, right? So the player is actually exploring, right?
Yeah.
So I guess I'm just asking if we look at like VH at a given time.
Why we're adding this bonus?
No. I was just going to say, like, so what is VH optimistic with respect to?
In the two-player zero-sum game, it's much clearer. It's like it's just optimistic with respect to the Nash value.
Yeah. Okay. Cool.
In the CCE, it's more complicated, as I said, because you have multiple CCE. I would say it's like optimistic in the final couple iteration against the CCE you're conversion to. That is my understanding.
Okay. Thanks.
Yes.
So can you extend this, or have you thought about extending this to the discounting case? And is something related to what you were just saying about this learning rate making that difficult?
Okay, the discounting setting, there's a triple way to do discounting setting. Is basically say I'm gonna truncate the discounting setting to some 1 over, like if I did discounted parameters gamma, then I can truncate the steps to 1 over 1 minus gamma. So basically, up to that steps, all the future rewards like too small, I don't care. And I can just directly apply these results to deal with this this kind of setting. If you're asking something that is like more restricted, like in the proper learning sense, like I want to have a policy that is independent of horizon, independent of steps. I want to have like a stationary policy. I think that one we can prove. I think the Clark's theory group has a recent paper which shows you cannot compute that in PPAD. It's like in PPAD. Even computing the stationary mark of CCD is PPAD. So that is, if you want to do improper learning, everything is easy. You just apply this one. If you want to do proper learning, then you can.
Are there any other questions?
Maybe in practice, even just for a single agent case, how does it compare performance to learning, for instance, experimentally? If you could,
we haven't run the experiment yet, but I would imagine it's probably similar, I guess.
All right, why don't we go ahead and stop there? We'll have a quick break until 11:30, and then we'll come back for Sham's talk. But yeah, let's thank Chi again. That was a great talk.
Thank you.